Today, we are going to continue looking at applications of integration. All of our applications are going to come from the same kind of source. Not the same source in terms of physics or economics or anything like that, but multiplication. We're going to think of integration as multiplication, but one of the factors is going to be variable. So yesterday, we found the area as length times width, but the length was variable the whole time. So let's look at a variation on that problem. Let's consider a plate bounded by the graph of y equals x squared, y equals 4, and the y-axis. Should be familiar from the problem that we did yesterday. The difference is that what's variable here is that the density of the plate at any point, y units above the x-axis, is given by 10 plus 0.5 y grams per centimeter squared. So what that means is that the density of this region is variable depending on y. So if we wanted to find, when we wanted to find the area of this region, we could have sliced it horizontally or vertically. We could have done the problem in terms of dx, or could also do the problem in terms of dy, slicing horizontally or vertically. That's kind of backwards. Slicing vertically for dx or horizontally for dy. But in this case, we don't have a choice. What's variable is not the length. We're not doing area equals length times width. We're doing mass is equal to density times area. And what's variable is not the area of the region, but the density of the region. So the density at this point is 10 plus half of whatever the distance y is. So here's the distance y. And the density is increasing. It starts off with a density of 10 on the x-axis, and then the density increases as we go up higher. What we want to do is calculate the mass of the plate. And we know that, and we have a variable density, so and we have an area. So we're going to use the basic multiplication. Mass is equal to density multiplied by area. So in this case, the density is variable. If the density over the whole plate was constant, we could just take the area from yesterday and multiply by the density and come up with the mass. But the density is variable, and that means we have to integrate. So if the density was constant, we could get away with just multiplication. But since the density is variable, we're going to have to integrate. Since the density is varying with y, we have to write an integral in terms of y. So that's all the thinking that happens before we even decide to do this process. So if the density was constant, then we would just multiply. But the density is variable, so we're going to have to integrate. Moreover, we're going to have to integrate with respect to y, because that's the variable with which the density varies. So since density is variable, we have to integrate. Since density varies with y, we have to integrate with respect to y. So we're going to have to integrate dy. So we can't slice it vertically in this case because the density is not varying side to side. The density is varying up and down. It's a different story if we were allowed to use more than one variable, but since this is single variable calculus, we have decided to limit ourselves and force ourselves to just use one variable. So we all like an extra challenge, so one variable it is. So the density varies with y. We have to integrate dy. We're going to do the same thing that we did yesterday. We're going to break this slice into, break this region into a bunch of slices. And on each of these slices, we're going to assume that the density is constant, even though there's some small change in y on that slice. This is the same plan that we always use when we're integrating. We look in the direction that things are being variable, and we decide that it's going to be constant for some small delta. Same plan that we always use. It's the same thing we do every night. Try to take over the world. I don't know if anybody's seen that show, but if you haven't, you should. A shameless plug for Animaniacs. This is not a sponsored video, but I just like Animaniacs because it was a great show. I haven't watched it recently, so I don't know if it holds up, but my recollection would say it's still a great show. And this is not in the perfect nostalgia zone because I wasn't 14 when I was watching this. Like, think about the stuff you liked when you were 14. You're probably going to like it when you're in your 30s and your 40s. And if you become a movie executive, you're going to be doing a lot of remakes of the stuff that you liked when you were a teenager. So, who knows? All right, so we're going to slice this horizontally because that's how density is. That's where we can hold density constant. If I sliced vertically and I tried to integrate dx, the density is variable on all these different points in this region. So that won't do. The density is constant where y is constant. So that's how I have to slice. And then I'm just going to slice it up for all the y's and then add up all the y values, integration style. Notice that I still have to do a lot of the things that I did yesterday. I still have to be concerned with the area. I still have to make a relationship between x and y. So to calculate the mass, we're going to have the density, and then we're going to multiply by the area, and the area is length times width. So now that we're slicing, we can't just take the area of the region. We've got to take the area of the slice. So we're going to calculate the mass of the slice. So I got to go up in here. I'm going to use delta y as the width, and I'm going to use the length as the length. I'm also going to smudge my mass. There we go. Now, everything needs to be in terms of y. The width is equal to delta y, so that's no problem. The density is 10 plus 0.5 times y, grams per square centimeter, so that's no problem. But the length, we have to write in terms of y. So we notice that the length is equal to x, but this is no good. I need delta y. And I'll just do the same thing we did yesterday. If y is equal to x squared, then x is equal to the square root of y. Now I can write all three of these factors in terms of y. The density, which is 10 plus 0.5 y. The length, which is the square root of y. And the width, which is delta y. You might notice that all we're doing is taking the integral that we had yesterday, the dy integral that we had yesterday, and throwing in the density. The reason that you notice that is that's because exactly what we're doing. Mass is density times area. Yesterday we did the area calculation, so it makes sense that all we have to do is throw in the density. But we have to throw it into the integral. We have to do it before we start integrating. We have to do it when everything's broken down into strips. We can't just multiply the fixed area that we had from the entire plate. So once again, we are concerned with an order of operations problem. Now we just need to integrate where the y, all the values of y, where we have a slice. And like we saw yesterday, the y's go from 0 to 4. So our total mass, this is the mass of the slice, so our total mass is going to be the integral of, we'll have the density, 10 plus 0.5 y. We'll have a square root of y for the length. In the definite integral, the discrete delta y becomes the continuous dy, and we integrate y equals 0 to 4, because those are the values of y for which we have a slice. So, if we want to quickly arrive at an answer, the best thing to do would just be to ask a machine to do the calculation for us. Oops, clearly I just had some non-real answers. I was doing non-real stuff yesterday. So we're going to math 9, our function. And I'm just going to type it like I see it, 10 plus 0.5 y times the square root of y with respect to y from 0 to 4. And it's like to 5 significant figures, we'll have 59.733 grams. Any questions? I was checking to see if the calculator knew this is a fraction, and it doesn't, so that's okay. So the process is the same that we used yesterday. We look where things can be held constant. In the case of area, it was horizontal slices or vertical slices, so we could integrate dy or dx. In this case, because of the way the density is set up, the density increases from y equals 0 to y equals 4. The density is increasing in the y direction. We have to integrate in that direction. If we allowed ourselves to use more than one variable, then it would have been okay. We could have put the density function in, and then the length could have been in terms of x. Then we would have integrated a dx and a dy. But we're only allowing ourselves to use one variable because we like a challenge. Any questions? So I guess the takeaway from this particular example is we need to set up our slices where we can make things constant. Slice where you can make things constant. Slice where things are constant. So that will determine your direction of how you slice things up. Any questions? Cool. one of the things that we want to point out about the integration. It's point number 2 that I wanted to make today. When you're writing your integrals, the endpoints are parts of the question. So when writing integrals, the endpoints are part of the question. Let's say definite integrals. When I set up a problem, it's going to say something like, find the mass of the plate, round your answer to 5 significant figures. The reason I ask for 5 significant figures is not because I care about the mass of the plate to 5 significant figures. I care about how you arrive at that number. But when I ask for 5 significant figures, the chances of you getting this right just by accident are pretty slim. No one's just going to guess the correct 5 significant figures. So that's really just a grading tool on my part, just for full transparency. So when you write up a problem for me, I say, show your calculations, and then I look at your answer first. If your answer is correct, then I just kind of like scan the rest of your work. I take a glance at your integral, and I say, yep, that looks right. This integral was from -2 to 7, so that will do. Must be going okay. And then I can tell if you're supposed to integrate this from -2 to 7 and you have the correct answer. And then I look at the integral and the integral is from 0 to 9. And I say, oh, well, clearly that isn't going to work. Then I look at what you're integrating. And if I don't see an x plus 2 or an x minus 2, then I know that you just wrote what you thought was the integral and then got the answer from your friend. It is super obvious when y'all try to cheat this process. So anytime you just copy and paste an answer from someone else, just assume that I can totally tell that you did that because it's super obvious. Like super obvious. The formatting is even weird. Some of you don't even like fix the formatting. It like copies and pastes, so there's like a bunch of extra boxes. It's like, oh, why are you double boxing your answers? And you're like, oh, because I don't know how to copy and paste properly. And it's just super obvious. Anyway, that's beside the point. But I just wanted to tell you, the next thing I look at after I look at your answer, the next thing I look at is the endpoints of the integral that you're writing. So let's take a look at another example, because this is death by example zone. And let's suppose that we have a hemispherical bowl with a radius of, let's say, 8 centimeters, contains water to a depth of 5 centimeters. Let's find the volume of the water in the bowl. So the previous problem was based on multiplication. Mass is equal to density times area. Just like the problems the day before were based on multiplication. Area is equal to length times width. Just like all the problems in this chapter are going to be based on some multiplication. Distance equals rate times time. Mass is density times area. Area is equal to length times width. Work is equal to force times distance. It's all based on multiplication. It's a multiplication in which one of the factors is variable. That's how it works. In this case, we're calculating a volume. It says find the volume of the water in the bowl. The multiplication that's going to be in play here is that volume is cross-sectional area multiplied by height. So volume is cross-section area multiplied by height. This is not actually a new concept, but it might be a new concept for some of you. So if we think about something like a rectangular solid, that has some length times a width times a height, we know that the volume of a rectangular solid is length times width times height. Volume is going to be length times width times height. And what we're doing is we're taking the cross-sectional area, length times width, and seeing that it is constant throughout the entire height. So we're really looking at length times width, or one way we can look at this is length times width is the area of the cross-section multiplied through the height. We also see this if we look at a cylinder. We know that the formula for the volume of a cylinder is pi r squared times h, where r is the radius of the cross-section of the circle that we see in cross-section. So here we have a height, and let's say we have a radius. We know that the volume of a cylinder is pi r squared times h. And all we're doing is taking the cross-sectional area of this circle and multiplying it by the height. We get to do this because the area remains constant throughout the height. Any circular cross-section of this cylinder, it's always the same circle with the same radius. Any cross-section of this rectangular solid is the same length times width times height, length times width. The cross-sectional area in each of these figures is always the same. The reason that we get to multiply is that the cross-sectional area is constant. So now let's take a look at our hemispherical bowl and see that the cross-sectional area is not going to be constant. So let's draw us a bowl. Aim for this one right here. Close the circle. I don't think I closed the circle before, but if you didn't see a demonstration of this thing. Plus the little center finder. Oops, I bumped it. Plus the little center finder acts like a little stand, so you can have a little chopper eye on your desk. I know not all of you have seen Stargate, which is just unfortunate for y'all. So I actually don't need this whole circle. I just like drawing the whole circle. What we need is a bowl, and we're going to look at this from the side. The way I labeled this and then put the thing right through, it's just Ike from South Park. And I need to erase the top half, or just move the top half so it's like, oh, don't kick the baby. So our hemispherical bowl, let's take the bottom part of this, and this is going to be a hemispherical bowl, and the radius is going to be 8 centimeters. And I'm going to fill it with water to a depth of 5 centimeters. The first most important thing to recognize is that the shape of the water is not a hemisphere. So it's the most important thing to note. The first most important thing to notice is that the water is not in a hemisphere. So it's 5 from in the center of the bowl. It's 5 units from one side to the other, but it's not 5 from going straight across. So we're not in the shape of a hemisphere. I don't have that. If I'm going to start doing some calculus stuff on this, I'm going to need to use the radius of 8, but that's going to require the center of this circle. I kind of wanted just this part right here. So look, if you cut the top and the bottom off of a tennis ball, you can't, if you cut like a 1-inch strip out of the middle of a tennis ball, you do not get to put the top and bottom parts together and make a sphere. Also notice that the sides here go straight up and down, but the sides here where we get to the water is going off at an angle. So it's not going to match up. It's not going to be continuous. So here's where the rest of the Pokeball was. And now you can see exactly why I have to use a circle tool to draw circles. So I definitely flatten that out. Oh, also not sponsored, but if you're wondering what kind of sorcery this is one of those erasable notebooks. And it is a, oh, I don't have it on this side. It's on the other side. I use a Rocket book for my notes because I was going through I went through like 8 pads of paper when I was writing notes before. So my wife got me for Christmas this awesome erasable Rocket book. The important thing is multicolor pens. So that's the important thing. All right. Not a sponsored video, not by Maker's Cabinet or by Rocketbook or by Pilot Friction pens. No sponsorships. These are the tools that I use. No sponsorships for Texas Instruments, even though these are the tools that I use. All right, what are we talking about? Oh, yes. So the important thing to note is that the water is not in the shape of a hemisphere. The water is not hemispherical. So I can't just do the formula for the volume of the sphere cut in half with a radius of 5. We don't have a radius of 5. We have a radius of 8, but it comes from here and goes to the circle. It does not start at the water. So what we're going to do is follow lesson from the previous example. The previous example is said, slice where things are constant. And if we look at this from the top, when we slice where things are constant, they're constant horizontally. So if you imagine the entire circle, if we imagine the entire sphere, if I want to slice where things are constant, and so if I slice down here under the water, a nice slice of water sounds nice and refreshing. That slice is going to be a circle. So I'm going to take the cross, this slice represents a circle. I'm going to take the cross-sectional area and multiply it by the height. Now, if I move up a little bit, then the height is going to be different. But to set up an integral, we assume that the cross-sectional area is going to be constant for some small change in height, which is the same thing that we always do. So I'm going to turn my cross-sectional area into a volume by multiplying it by some small change in height. So the volume of the slice is going to be area multiplied by height. The area is going to be pi r squared because the cross-sectional area is, the slice is a circle. So the area is going to be pi r squared. And then the height is going to be my delta variable. I'm going to just call it delta h for some small change in height. I'm going to go back here, and then this is this horizontal slice is a circle, and it's going to have a variable radius. That's the part that's always changing. Its shape is constant, but the size is not. It's always a circle, so I can always use pi r squared, but I can't use the same r. Any questions? So at this point, we have to go back to our finding the area of a circle. And we have to decide where we're going to put the variable h. I said this is going to be some small change in height, but I didn't say where we're going to define the quantity h. Fortunately for our heroes, we have many choices about where we define h. Unfortunately for our heroes, we have many choices for where we define h, and now we have to choose. I'm going to give you the most common place that we put the delta h. If you recall from the first problem that we did, where we found the area of an entire circle, we got a relationship between the horizontal stuff and the vertical stuff by drawing a right triangle from the center of the circle down to the slice, using the radius of the circle as the hypotenuse. So this purple triangle, I don't know if you can tell if it's purple, but that's just because my camera is not picking up enough color to recognize the vibrant purple ink of my Pilot friction erasable pens with stylish color matched barrel. But seriously, this is not a sponsored video. If I pull out this, I'm going to have to label this includes paid promotion. Yeah, I missed. We've got the hypotenuse of this right triangle is an 8. This is why we have to go from the center. If we go from the surface of the water, I don't have a hypotenuse that's constant. Hypotenuse is variable. But if I go from the center, then the hypotenuse is always the same. It's always 8. I've got my radius down here. And so I'm going to just use this other leg of the triangle as my h. So I'm going to say h is this distance here. It's the height. Goes from the center of the circle to the slice. So I'm going to let h be the distance from the center of the circle. Oh, sorry, center of the hemisphere say the center of the top of the bowl to the slice. So in the picture, that'll be this h up in here. What we always have to remember to do, we've only had 2 examples to see this, so we've got to go back, we've got to make sure that when we define our variable, that establishes where 0 is, and it establishes the positive direction. So once I say that h is going to be the distance from the center of the top of the bowl to the slice, I've said that h equals 0 is going to be up here at the top of the bowl. That sets the bottom of the bowl to be at h equals 8. That establishes down as the positive direction. And more importantly, it establishes the surface of the water to be at 3. So when we go to set up the integral, we're not going to be integrating from 0 to 5 because we don't have water from 0 to 5 in terms of h. We have water from 3 to 8. 3 to 8 is the 5 centimeters of water that we're dealing with when we set h to be this distance. So this tells us that our integral is going to be from 3 to 8, not from 0 to 5. So now all we have to do is write r in terms of h using the Pythagorean theorem, then set up our integral. Pi times r squared times the delta h, integrate from 3 to 8. We're going to lead with this problem tomorrow, write the integral. So your job before tomorrow is to write an integral. And find the volume. So your job will be to write an integral and find the volume. Notice that your integral is going to go from 3 to 8. Then just for a preview, the other thing that we're going to look at tomorrow is, like I said before, we set h to be the distance that we set it at. I mentioned that I could set h to be wherever I want it. So what if I want it to be somewhere else? Can we write an integral where we integrate from 0 to 5? So the question is, where do we put h? And then think about how it changes the integral. Because what we're doing is, the important part of this problem is not finding the volume of the water. Because to find the volume of the water, we wouldn't calculate it. We would pour it into a graduated cylinder and then measure it. But this is all hypothetical math class. We don't have access to the labs, and we're in lockdown anyway, so we can't go onto campus. So we're going to have to do this boring Mythbusters style. I don't know if you ever saw the show Mythbusters, but a lot of the questions on Mythbusters are solved with math. But that's boring. No one wants to watch that. You'll have a hit show if you actually shoot things and blow them up. But if you just like do things like in, I don't know, school, then no one's going to want to watch. You know what I mean? Especially at 9 weeks into the semester where everything's online. And you see in the syllabus, like, oh, wait a second, professor does not require video to be on because he finds it invasive. So in the beginning of the semester, you're just like logging on like for a couple weeks, maybe you pay attention. Then you just kind of like log on and go back to bed or log on and make your coffee. And then somebody's like, oh, hey, I didn't log on a couple days ago and he didn't even notice. And so those students that have noticed that are still sleeping. That's okay. That's why I record this. So yesterday's didn't get posted. I think I closed the window on YouTube before it was done posting. And so things didn't get posted. So yesterday's videos and notes will be posted today. That's it for today. I will see y'all on tomorrow, and thanks for playing.